Okay, hello and welcome. I will be explaining BMO2 2019 question 1. The question says, let ABC be a triangle. Let L be the line through B perpendicular to AB. So this line here is L. The perpendicular from A to BC meets L at point D. So that's this line. The perpendicular bisector of BC meets L at the point P. So this is the perpendicular bisector, and this, of course, is P. Let E be the foot of the perpendicular from D to AC. So this is the perpendicular, and this is E. Prove that triangle BPE is isosceles. To prove this, I will prove that there is some circle that goes through both B and E and has a center P. So we know that PB equals EP because they're both the radius of this circle. Okay, so we start by proving that ABDE is a cyclic shape. We know this because angle AED plus angle ABD equals 90 plus 90 equals 180 degrees. And we know that shapes, quadrilaterals are cyclic when their opposite angles sum to 180. So ABDE is cyclic. From the fact that angles in a triangle add to 180, we can show that angle BAD equals 90 minus angle ABC. This is because we have this triangle that I've highlighted in green, and since angles in a triangle add to 180, we can say that angle BAD, so this angle, equals 180 minus 90 minus angle ABC, giving us this equation. Okay. We can also say that angle BED equals angle BAD, which of course equals 90 minus angle ABC from above. Okay, so we say this because we know that there's a circle that goes through all of these points, as this quadrilateral is cyclic, and so these two angles here and here, they both subtend the same arc BD. As we know, angle AEB equals 90 minus angle BED, we can prove that angle AEB equals 90 minus 90 minus ABC from this equation, giving us ABC. So, okay, so therefore angle EBA equals 180 minus, or angle AEB minus angle BAC. So this is simply because angles in a triangle add to 180 degrees. Equals 180 minus angle ABC minus angle BAC. But we know from this triangle ABC that this equals angle ACB, this remaining angle here. And therefore, angle ABC equals angle BEC. AB must therefore be tangent to the circumcircle of BCE. So that's this circle. Sorry, it's not very good. because of the converse of alternate segment theorem. So alternate segment theorem says that if you have a circle, so in this case the yellow circle, I'm highlighting green, that this angle equals this angle of a triangle, the opposite angle of the triangle. But we can use this in reverse to prove that this line must be tangent. And because angle ABC equals angle BEC, as we proved here, this line AB must be tangent. From this, as we know that the radius is always perpendicular to the tangent and L is perpendicular to the tangent, we know that the circumradius is some line segment along L, and therefore the circumcenter must be some point on L. Okay, the circumcenter must also be equidistant from points B and C on on line L. So we know that all points that are equidistant from B and C lie along this perpendicular bisector. This is quite a simple fact, and it uses congruency to be proved. So these two lines, if you have this point here, form two congruent triangles. So you've got this one and this one. Therefore, this length equals this length. These two triangles are congruent because as it's a bisector, this line here and this line here are equal, and well, you have the two angles at 90 degrees, and so by RHS congruency that this point must be equal to both sides. Like equidistant from both points. And so the circumcenter must be the point where this perpendicular bisector meets L, P. So P is the circumcenter of this circle that goes through ECB, and so EP equals CP equals BP, which is the circumradius. And as EP equals BP, triangle BPE must be isosceles. Okay.